Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Cheers. Today I've got a set of PCBs here to assemble. Well, one of them anyway. Always love seeing that there. I don't know what that actually means. Or ho. It's beginning to look a lot like Christmas. Shit everywhere. Anyway, so let's get this box open and have a look at what we got. So neatly packaged as usual, and this is what we're after. These are the PCBs to my MOSFET amplifier that I did in a previous video, or two videos, which I'll link in the description, and it now finally has a PCB. So let's open up the bag and get a PCB out so we can have a good look at what we've got. Speaking of Christmas, which is coming up very quickly, getting a set of new PCBs from PCB Way is a lot like Christmas every time. Okay, so here's one of the PCBs there, and it does actually look quite sexy. I'm pretty pleased at how that turned out. And in this PCB's case, I've decided to go with putting the reference numbers on the components rather than their values. I don't know, I chop and change between doing either the reference numbers or the part values, but it makes it actually easier to put in things like capacitors, electrolytic capacitors. Because for example, C11, which is actually a 100 microfarad 63 volt, putting 100U/63 volt takes up quite a fair bit of space on the silk screen, and it would have to be above the capacitor because it won't fit within the circular circumference of the capacitor. So then that leaves you with less space up here to put another component close to it, such as in this case like C8 if the value is there. So it actually makes it more compact when laying out the parts close together like this, so you've got less wasted space, I guess, on the PCB. But anyway, now there's one thing about this. I will release it if it works as a shared project. However, these output MOSFETs, you can only source them from one place, and that's a website in the UK called Profusion, and they're fairly expensive. They're about, I think it's $18 each Australian for one of these MOSFETs, either the P or the N. And get this, the shipping is $45 Australian. Yeah, it's expensive. No one makes lateral MOSFETs anywhere anymore. Hitachi stopped doing it years ago, and if you happen to find a couple of the 2SJ or the 2SK MOSFETs that would work in this circuit as well, they're most likely going to be counterfeit unless you can find, like, you know, original new old stock. The 10N20 and the 10P20 MOSFETs you'll only find from Profusion, and currently the P channel ones are not available from Profusion. They're out of stock. They are still an active component. They haven't been made obsolete. I've actually got in contact with Profusion, and they have told me that they expect to get a stock of the P channels by February 2026, which is quite a fair way away yet. It's just something to do with manufacturing issue. I'm not sure what that means. They didn't go into specifics. They probably don't know themselves, but they're having issues at the factory with the manufacture of the P channels. They have currently, the last time I checked, about 1,000 of these N channel ones. But that's pretty useless if you don't have the P channel to go with it. Now I also don't have a bracket. It's just a 100mm long by 32 by 32 3mm thick piece of aluminium L bracket stock. I don't have the two Zener diodes, 10 volt Zeners that are required. I'll have to get them. I also don't have the 1K trim pots that go here and here. I have to get them as well, but today I can assemble this up as far as I can in time lapse, including the output resistors, etc. And then we'll talk about this down here, L1, which is the inductor that goes across a resistor in series with the output, just to help with driving capacitive loads. I'll show how to wind that. However, I can't test it today because I don't have the bracket, don't have the trim pots, don't have the Zenas. But at least I can get something done today, is what I'm trying to get at. I think I'm also missing some bipolar capacitors. Yeah, I'm going to have to get them as well. I completely forgot about that. I'm not exactly prepared. I'll have to look up what C3 is. I think it was 100 microfarad. So I'm going to have to get a 100 microfarad bipolar. Let's talk about it properly. And I also have to sort out the parts that are on this breadboard, because all the resistors and stuff, these are the wrong value trim pots, are already on this breadboard, and yes, it was 100 microfarad. So I'm going to have to get a couple of capacitors from JCar as well this week, apparently. But that's alright, those extra components can be slipped in after the initial assembly is done. It's not much of a great big issue. So before I assemble this, let's have a quick look at the schematic so I can just talk about some of the changes that have happened over the last few weeks since the original videos were published, and then we'll get into assembling it.
So here's a look at the schematic. The only changes I've made to it really are two things. I've added a constant current source here for the long tail pair, and we do have the offset adjustment as well. But over here I've got a clipping detector. Now this circuit is borrowed from the Playmaster Pro Series 3 amplifier that I recently repaired, and this circuit does actually indeed work quite well with this particular amplifier because it's of similar design. And I also found it does work on the Elector PA300 as well, but that requires further testing. Basically what this circuit does is, this is a common emitter amplifier, and we're looking at point B, which connects to this part of the VAS stage over here, which is actually the error signal, or the error side of the amplifier, so the negative feedback side to the long tail pair, because it goes into this transistor here. So we're measuring off at this point, and once the voltage here at the base is sufficiently high enough to bias this transistor on, because there's no other biasing at all, well, this transistor will conduct, allowing current to flow from its collector to its emitter, in turn turning this second transistor on, which will light the LED. Now, once that transient goes away, well, the LED is going to go off instantly. So when we have the transient, this capacitor C13 here, the 100 nanofarad, charges quickly, and once the transient disappears, well, the capacitor can now discharge slowly through the base and emitter junctions of this transistor here, and allowing this LED to go out after a certain period of time, like 200, maybe 300 milliseconds, something like that. Because audio is dynamic, so for the clip LED to blip is going to be not noticeable as if it was on for a short period of time and then goes off. So that's what that does. And it's a very simple, elegant circuit, and I don't see any reason not to use it. I've got 220 ohm resistors here at the gates, and I've chosen 10 volt Zenas here for the gate drive limiting circuit, so we should never have any more than 10 volt at each of these gates in the event of, say, a short circuit on the output. I've marked L1 as 0.7 microhenry. Well, at the end of the day, if you use 12 turns of 1.25 millimeter diameter enamel copper wire, that was hard to say, on a former of roughly 10.5 millimeters, say a AAA battery, and the coil will end up being roughly 15 millimeters in length, it will require 500 millimeter length of the enamel copper wire. and we will end up with around about 1 microhenry at the end of the day, which is perfectly fine. All this circuit here with its resistor is to help prevent this going into oscillation when driving difficult loads such as a capacitive load. Other than that, there's not much to talk about this circuit. Most of it was discussed in the first 2 videos when I was building, trying to fault find why I had a DC offset, etc. So they're linked in the description. If you haven't watched them, go ahead and watch them. And of course, point A of this clip detector just goes to the positive rail at point A here. And that's basically it. But the LED is marked as LED 1 on the PCB, but it is actually designed to be on the front panel. So at the end of the day, you would probably put a header connector or just solder 2 wires to the LED point on the PCB, run the length of wires to an LED at the front panel and like glue it in with, say, contact adhesive or araldite, something like that. Other than that, I'm going to start thinking about assembling this thing.
So that was a look at the schematic, and now I'm going to begin assembly of this in time lapse, and you can come along for the ride and watch me assemble this. Soldering iron is off, so I turn it on and just walk away. Well, that's about as far as I can go with assembly for the components, because I don't have the 1 watt resistors, the Zener diodes, the trim pots, and a couple of various other different capacitors, which I completely forgot about. I also don't have the fuses either. And I haven't put the 0.22 ohm resistors here and here either, because, well, when I go to put the Zener diodes in, well, these are just going to be in the way, so it's a lot easier with the largest components, which is these, not like, you know, sitting right up next to where I want to, you know, work. So that can wait till very, very last. Everything is soldered for the most part, so I'm going to now turn the attention to the inductor here. Now the inductor requires 12 turns, roughly 10.2 millimeter diameter of inner diameter of the coil, of 1.25 millimeter enameled copper wire. Now that's the J-Car catalogue. It's WW4024, but you can find this probably anywhere online anyway, so it's not really specific. 1.25 millimeter is kind of on the thick side. It just barely barely fits through the holes in the PCB. Just very, very tight. If anything, if you wanted to, you could probably get away with 1mm there. The total inductance is around about 1 microhenry, so it's between 0.7 and 1 microhenry is fine, so it's not overly critical. So I've worked out that I'm going to need about 500mm long of this stuff in order to make that inductance and then the required number of turns. So I don't like winding coils with, you know, a spool like this, so I'm going to measure out roughly 500mm and then I'm going to cut it off, and to actually make the coil I'm going to wind it around the body of a AAA battery, which works out to roughly a diameter of 10.3 on the inside of the coil, which is perfectly fine. So I'm going to cut the wire and I'm going to start by baring the ends, but I'm not going to tin where I've bared the end because it will not fit through the PCB then. So I want to make sure that I can actually get it in the PCB before trying to tin it, and this stuff is not really enamel anymore. Can be rather challenging to get off. You could scrape it with a knife, but yeah, even scraping it with a knife can make it nearly impossible to actually get the solder to take to it, so it really needs to be really cleaned off properly, like with a file or even a bit of sandpaper would probably do. So let me get set up for winding the coil and I'll come back in just a minute. So I've got my wire cut down and I've got a piece of 40 grit sandpaper here, which is as coarse as I've got. So I'm going to go around about roughly the last 10mm of this, and this might prove a little bit more awkward to do. I think that's pretty good for the most part. Reason I chose 1.25mm is because it's nice and thick and the coil won't just spring out after you've wound it, so it kind of holds its shape just nicely. Plus it requires less length and diameter of coil to make 1 microhenry. So with that in mind, that's going to be my starting end. So I'm going to start by putting that close to the battery here and make my first turn. Now it doesn't matter which direction you turn it in, but keep a count on the number of turns you've made and try to keep it closely spaced as possible. So that's 1 full turn. That's going to be 2 turns, 9, 10, 11 and 12 full turns. There we go, 12 full turns. Now it's fairly wide, but I've designed it so it actually stands vertically, so that means this end that I've bared now has to be bent at right angles, like that. And then I'm going to bend this over and pass this end through to the other end, but to help compress this coil down a bit more, I'm going to put a couple of zap straps on either side here just to hold its shape. Now this may seem like a waste of the zip ties, but the thing is I could always still leave them on the coil when I'm finished and leave them on there as I'm soldering, so it still maintains its shape. Which is probably what I'm going to do, but the amount of heat going through the copper wire may cause the zip ties to melt, and this is very fiddly, but it's doable. So yeah, I think that's going to be acceptable. So I'll just make sure that one is tight and that one is tight. Well, it is now. Okay, and then I'll cut off the excess zip tie length. Don't need that battery anymore. I mean, it's not exactly perfect, but it'll do. So then I'll bend this over on itself, pass it through the middle, and I'm probably actually going to remove the zap straps when I'm finished, because it's just deforming the coil anyway. So it's going to be probably the ugliest coil in the world, but as long as, you know, you can solder it in the board, then all is good with the world. So trying to get this to bend over on itself, and it just does not want to do it. That's good enough for the most part. So what I have to do is then trim this down a bit. I'll just take off that much. I've got to sand off this part as well so that that's bare, and then I can present it to the PCB. Yeah, I think I am going to remove those zip ties. I think that's good for the most part. I found a small file works better. Okay, so I'll get rid of these zip ties now, and then I'll offer it up to the board so it now relaxes the coil, and I can, you know, manipulate it around so it looks a little bit neater. For the most part, yeah, sure, it's ugly, but it'll do the job. Now this may take considerably a fair amount of heat, and I've lost my solder now, which I'm starting to run out of. But yeah, so we'll solder this, and then I'll make sure I've got continuity across the coil. And yeah, it's ugly, but it'll do the job. So just leave it on there for a little bit there, and then I saw the solder go bloop. So that indicates to me that it is actually taking, or has taken, to the copper wire. Cut the ends off. And for 500 millimeters, I only wasted about 30 mil. And that's the coil in, nice and tight. So it's not the prettiest looking thing in the world. See, it's not pretty, but again, it doesn't have to be, as long as it does what it's supposed to do. So I need to now make sure that I've got continuity across that coil, or else it was pointless it being there. So I'm going to continuity. Oops. It doesn't appear I got continuity at the actual solder joints. That one I do, but not right down there. I'm actually measuring it from the top solder pads and the speaker connector. It is continuous. It must be just a build-up of like this flux crap. It is continuous. I just want to know what the actual resistance is. According to my meter, it's 0 ohms. Perfect. Or about 0.1 of an ohm. Alright. So that's good. I'm going to clean this up with some IPA and a toothbrush when I can find the damn thing, and a bit of a Q-tip just to like clean that area of the board up, of the flux. because I've now scraped it. It looks a little bit, you know, crystalline. See how it looks crystalline? So I'll clean it up and I'll come back in just a second. 0 ohms. I say that's a win, 0.1. Move it around a bit. If I push hard with the probes, we get 0.1 of an ohm. Okay, that's fine. I'm satisfied that that is continuous and has got continuity through the coil. So that's about as far as I can go today with the assembly because, well, I don't have the rest of the parts. It may be a little bit more awkward now to get things in with the coil in, but yeah, it turned out to be more like 15mm diameter, more than like, you know, 10. That's just what it is. I mean, I could have probably used a smaller bit, but we're looking at, yeah, close to 15mm of diameter there. But that's fine, I guess. So I need to get the rest of the parts, the 210 ohms, the 12K, the capacitors, and the xenodiodes, trim pots, and then I can complete assembly and begin testing. So that's about as far as I can go right now. I actually ended up changing the coil because it looked ugly. I didn't like it. I've actually now wound 12 turns of the 1.25mm copper wire around a 6.5mm drill bit around its shank, and that gives me an overall diameter on the outside of roughly 9.1mm, and it actually sits in the board with less interference. So that's what I think we're going to go with. So basically what I said before about winding the original coil is now practically useless, but I think that will work better. However, if anyone has got any idea what sort of solvent or acid or anything that can actually dissolve the coating on the wire here, make it easier than just scraping the stuff, let me know in the comments below. I've got updates. I now have all the components installed because I went out to JCar this morning, bought all the rest of the parts I needed, and populated the board accordingly. Now, it is actually now ready at a certain point for testing, but I still don't have the bracket to mount the output MOSFETs to, but that's never stopped me before because I already have a set of MOSFETs mounted to a heatsink with some fly wires on it that I can just simply solder the wires to the pads. Now, I don't need both sets of MOSFETs to test this. I only just need one set of MOSFETs connected. So before I do that, I'm going to wind this bias pot all the way anti-clockwise so it's at minimum bias, and because I don't want heaps of current going through the output stage. And I'll put it on a power supply that's limited to 200 mA after I've soldered the fly wires, there should be enough turns, fly wires to the pads. Well, I've got the output stage MOSFETs temporarily connected to the top pads on the PCB, rather badly, but they're on there. And the two 5 amp fuses are installed. I've got the power supply leads connected, plus my multimeter connected to the output point, so I'm measuring the DC content on the output. Got the power supplies roughly limited to 200 mA at plus minus 30 volts, so I'll turn the supply on. The circuit is not loaded except into the multimeter. 8 mA of current draw, excellent, good sign. As for a DC offset, 11 millivolts or so. That's not too bad, but I haven't adjusted the DC offset pot, which is right there in the center. So if I find out where my screwdriver is, which is over here, and I start twiddling this potentiometer whilst watching the multimeter, we'll see if we can get that offset to come down. So I'll turn it anti-clockwise, it's going up, so I'll turn it clockwise and it is coming down. Just gotta let it settle out. And if I keep going, we're down to about 5 millivolts. And if I keep going, we're almost there. I'm going to pretty much say that that's bang on. Excellent. Next question, will the bias adjust? So using the current meter on the power supply as a reference, I'll just come in and rotate the bias pot clockwise and see what happens. Absolutely nothing at the moment. Oh, it's coming up. Alright, excellent. There we go. So for initial testing, I'm just going to leave it around about a bias of that. That's perfectly fine. Our offset's gone up to about 0.8 of a millivolt, which is, yeah, okay. So I'm using the packing material that came with the PCB box as insulation, so it's not sitting directly on the desk, causing any issues. Like any metal on the desk may be shorting things out. But so far, these tests, everything appears fine. So now, I've got the bias set and the DC offset set. I guess it would be a good idea to actually pump a signal in and look at the output. Okay, I've got the function generator at 1 kilohertz hooked up to the input and the output hooked into a 8 ohm dummy load, and the scope's measuring across the output. So I'll wind up the gain of the oscillator, and we do have an output. However, well, it's going to do that because we've reached current limit. So that needs to be changed to 1.2 amps will do. And I'll up the other one a little bit too. Let's wind up the gain. Well, the circuit seems to be, there we go, there's clipping. We haven't reached current limit, so that's alright. About 14.9 volts, which is fine for the voltage I'm pumping into it. Drawing about 820 mA. Nothing smoking or has gone bang. But the amplifier looks pretty stable. There's no spurious oscillation going on. So, as far as I can tell, this is actually working as it should. So next it would be a good idea, I'll just kill the oscillator for a minute, to test the clip functionality. So I need to plug in an LED into that position here. I'll power the circuit off first before doing that, and then I'll drive it into clipping and see if the LED lights up. Got an LED installed, and the packing material underneath is quite handy because it allows me to poke the pins directly into the packing material, bend the LED over, so it should be making perfect contact with those pads. So I'll repower the circuit. Nothing really unusual happened, but the LED there did blip for a sec and then went out, but that's fine. So if I drive the amplifier into clipping, there's clipping there. I'll back it off and we look at the LED. I'll drive it back into clipping, LED is on. Back it off out of clipping, LED goes out. Now we'll notice one thing though. It's currently asymmetrically clipping, so it's clipping at the bottom first before it's clipping at the top. And we're not in current limit, so that's probably just tolerances of components in the circuit. But what that clipping detector is looking at is mainly the positive going side of the signal. So when it goes positive clip, as we can see it's now more symmetrically clipping, LED is illuminated. So if I back that off, it goes out. But we're still asymmetrically clipping. Alright, so it's passed those tests, and the transformer in that bottom supply is really starting to growl. So what that means now is I've just got to wait for the bracket to turn up, and then continue on this video with drilling the bracket, mounting the MOSFETs, and then finally testing the thing again. So I'll pick this video up once I've got the bracket. It's already been ordered. It won't be here for about a week. Don't know why that's making so much noise. That's why I hate EI core transformers. Well, it's been about 2 weeks since I did the first part of this video. The bracket has finally arrived, and surprisingly this time it's come from the same supplier, Hardware Master on eBay, where I've got those other brackets before. It comes in a box. Well, that's special. So let's open the box, and bubble wrap! Oh yes, I think this is more fun than what I want. Oh yeah, I love bubble wrap. Yeah, I'm going to have fun playing with that later. So anyway, let's get the bit that I need. So this is 100 millimeters long by 32 by 32 and 3 millimeters thick. Thank you. We're glad to be part of your project. Well, thank you very much, Hardware Master. I'm glad to have you as part of my project too. So let's get this polythene bag open, and I'll dispose of it thoughtfully. And by thoughtfully, once I can get the bracket out of the bag, I mean I'm going to throw it straight in the bin. So now what I have to do is I have to make sure that this actually fits on the module without too much issue. Yeah, it fits on there perfectly, so the measurements aren't off or anything like that. So that should be exactly 100 mil long, maybe plus minus half a mil or so. It says that it's 100 mil bang on, so I'm happy with that. So I have to then tape this up. I might do it on this face because it's easier. Tape this up, mark it out, and drill it, and mark this face as well that goes against the heatsink, and drill that. So I'm going to drill holes 20 millimeters apart on both sides, but these ones here on the heatsink bracket side will be, well, the heatsink face side will be like somewhere towards the center of the material. Maybe from the aspect of this, like center of this, from that point. Which, if that's 32 mil, that should be like 29. Yeah, 28.5, something like that. Okay, so let me get to marking this out, and then we can drill it. I hope you enjoyed that little high-speed drilling montage there that I did. So I'm ready to mount this. One of these holes for the mounting to the heatsink itself was a little off. Actually, I think it's that one that's off. It's quite off, actually. I just have to keep that in mind when I actually go to drill the heatsink itself, is to make sure to use this as the template of where the center of the holes are, so that it doesn't end up crooked or you can't get a screw in. The actual board side mounting face for the transistors look alright, and the transistors will mount just fine across there, and the holes in the PCB should line up with the bracket if I measured correctly, which they do. Don't know if you can see the holes, light through the holes there, but they are there. So the first thing I need to do is find out what I did with the other set of MOSFETs. I've got another two, and because I've soldered wires to these ones, I'm going to have to clean the ends of these off. So I might clean the ends of these two MOSFETs off and then locate where the other two are. I've cleaned those up as best as I can, and I found the other two MOSFETs. That one's a bit scratched. And thanks to Jeff that sent me these sets of MOSFETs, including the 2SJ and 2SK ones, about 2 odd years ago. They finally found a use in this amplifier module other than the Elliott Sound Products P101 amplifier. But yeah, thanks to Jeff for that. These ones have been soldered to, and these holes are perfectly clear, so I'll stick these ones that have already been soldered to in the unsoldered holes here, because these outer ones have been soldered to, so it makes it difficult to get them in. They may snag. So I need to work out where to bend these, and I also need to work out which one goes where. Alright, well that was pretty easy. The N channels go on the left side of the bracket and the P channels go on the right hand side of the bracket. So I'm going to make sure that I get the right channel on the right side, being the N channels go on this side and the P channels go on that side, like that, with the bracket in between. Alright, so I now need to work out where to bend the legs. I'm pretty sure it's going to be close to the shank. So let me just work this out off camera. Well, it works out to be about 1 millimeter away from the end of the shank here. So I'll just carefully bend each leg about 1 millimeter away from the shank, close to it. And then I can straighten them up in the other direction. Okay. Make sure they are bent at right angles, close enough. So this is my N channel. So that goes on the left hand side of the PCB. So it's going to go in the middle there. So I'm going to take a condom, a isolator, and I'm going to pass a screw through the transistor, through the isolator, off the bracket up to the board and pick the two up. I'm going to try and get all parts to go through all holes at the same time, which might prove a little difficult, but I got there. Okay, so that's one transistor on the bracket, and I can put a little nut on the other side. Just loosely, don't want to tighten it yet because I want to be able to move this bracket around, plus the sill washers. So I need to repeat that another 3 times, putting the correct transistors in the correct places, and then I can probably tighten them and then solder them. Alright, the output transistors are loosely mounted, so I can, one, make sure that my bracket is square with the board, and just loosely tighten these. And as I always say when doing output transistors and such like this, when it's mounted to, well, the board itself or a bracket like this, is to tighten down the transistors first before soldering, or else you can damage and crack the device. Just going to make sure those sill pads line up. They do, they are crossing over each other slightly, but that should be fine. Not really particularly worried about appearances, just as long as it's functional. So, tighten one at a time. Keep an eye on my bracket alignment, which seems alright. Tighten the other end. Probably should use a nut driver on the other side of this, but that'll scratch the MOSFET. That should be it. That looks good. So now these can be soldered. And snipped. There we go. I'm happy with that. I'm just going to make sure they are so it doesn't look like from my angle that they are like there's a hole around them, but no, they are soldered. And yes, I know this inductor looks like an erection standing up off the board, but it's functional. Now, I guess it would be a good idea now to hook this up to the power supply, mount it to a heatsink, and just test that the thing works. So that's going to be my next step. After I verify that it is isolated from the heatsink and the sources, apparently. Nothing is appearing to be shorted. Even the screws are isolated, so because of how they're positioned in the heatsink bracket, they're away from the actual sides of the hole or holes. So okay, let me hook this up to my bench supply and a heatsink, etc., and we'll do the power on test and see if it goes bang. Okay, the module is hooked up to the power supply. Just going to double check that I've got everything connected correctly. That's VCC plus, VCC minus, 2 grounds. This is the negative lead to the multimeter, and that's the positive lead to the multimeter, which is measuring the voltage on the output. Supplies are set to plus minus 31 volts respectively, and current limited to 200, at least on the top supply. MA, that is, just in case something catastrophic happens. So I'm going to turn the power on. Nothing unusual happened. Got about 50 mA of current draw on there, which is for the bias, which I can't remember where I actually had it set to. I might actually back that off a bit, because now there's probably like 2 extra output devices, so it's probably getting a little bit more current. 40 mA will do. DC offset is good, it's around about 3 millivolts, but that could probably be tweaked out. So I'll just tweak the DC offset pot. Which is fiddly. And this will probably have to be done again when it's at a higher power supply anyway. Yeah, that's good enough for the most part. I'm going to call that 0. Excellent, so it's passed the power on test. The current has decided to creep up a bit. We're now at 43 mA, but that's fine. DC offset's hovering around 1 millivolts, so I'm happy with that. So what I can do now is load the amplifier into a dummy load and make sure that it can produce power. And then, well, I'll put it into a speaker and we'll give it a sound test. Amplifier is loaded into 8 ohms. Current limit has been changed to 1.5 amps. Turn them on. Excellent. So we have a quick look. See if we get an output. Yes, we do. I've got the wrong time base. Here we go. Alright. You can watch the output stage while I increase the watts. Excellent. We've got the clipping. Out of clipping. We're pushing 16.8 volt RMS, so around about 35 watts into 8. So I'll reconfigure this for 4. Like so. Again, you can watch the output stage while I increase the watts. There's clipping, but I've reached current limit, so my current limit is not high enough. 2 amps should be good enough. There's asymmetrical clipping, clipping, out of clipping. Excellent. 13.6 volt RMS, so around about 45 watts. So good, it's passed those tests, nothing smoked. MOSFET's got barely warm. Okay, cool. So I guess it's now time to hook it up to a speaker and see how it sounds. Incidentally, the quiescent current has crept up to 48 milliamps now, but as it's cooling, the output stage is cooling down, it's dropping off. That's reasonable, I suppose. Well, I've got a speaker hooked up to it and there's no input signal yet, but it's turned on and there is a bit of a buzz coming out the speaker, mainly because of how everything's wired, but okay, that's working. Right, so let me hook up an audio source and we'll have a sound test. Alright, I got the input connected, but it's a bit buzzy, mainly because of layout, etc. of the wiring. But that's fine. Let's play a track and see how it sounds. Okay, that'll do. I'm happy with its performance. It does sound a little bit sharp on the treble, but that can always be corrected by a interconnected preamp. Now, what am I going to use this module for? Well, I do have plans for another project, which will be more likely in the new year now. This will be a monoblock and it'll be mounted into a case with a transformer, but before I do that, I really want to get hold of a 35035 transformer so I can A, test a power supply module for the Elector PA300, and as well as test that amplifier module at plus minus 50 volts, is test this one at plus minus 50 volts, see what its power outputs are, see if it self-destructs, you know, stuff like that, and then build it into a project case with, I'm going to not reveal what I'm going to actually be putting before it. That'll be something to be discussed later. But that'll be in a separate video of me testing this at a higher supply rail. I've got this at plus minus 56 volts maximum, which should be fine for the current transistors chosen. So yeah, I'll pick this video up again and retest it later. Now, I'll put in the description links to where you can get the power MOSFETs from. Be aware that there's a lead time of about 6 weeks now for the P channel ones because they're out of stock. So you're looking like mid-February now, next year, 2026. So yeah, the MOSFETs P channel ones anyway are kind of a little bit harder to get hold of at the moment, but they will be available. And I will put a link in the description in a few days' time after I've written the article of this of, you know, a purchasable PCB. So if you want to build it, you can order it from PCBY, the same, you know, the usual. However, be aware that you're going to be spending up to over $100 AU just on the output stage, including shipping. So it's going to be a pretty expensive amplifier module at the end of the day. But if you're not subscribed, subscribe now if you want to see this released as a PCB way project, because I'll put a community post on my channel when that PCB is available for purchase. I've just got to have time to write the article. Anyway, that's going to do it for this video. I hope you enjoyed watching it, and I hope you enjoyed seeing something that came from a breadboard come into fruition on a proper PCB. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.